All right, we've got one more vertical asymptote example to do before we move on to horizontal. Let's see. All right, well, sorry, I'm having some issues with my pen, but I'm at home, not at school, so I don't know what I can do without it. All right, so for this last example, the limit as t approaches 5, so the limit of t plus 2 over the square root of t plus 4, all of that minus 3. So same as always, we're going to plug it in. So the top becomes 5 plus 2. The bottom becomes the square root of 9 minus 3. So we get 7 over square root of 9 is positive 3. 3 minus 3 is 0. No surprises there. We know that means we have a vertical asymptote. So again, we're going to check the limits from the left and the right. So the limit of our function t plus 2 over the square root of t plus 4 minus 3. The limit from the left, if you're sitting there and you're like, oh, do I have to write this out every time, the limit notation? Unfortunately, the answer to that is yes. We really have to be clear how we communicate. So the limit from the left, again, I don't want to mess with the numerator. I want to leave that 7 in the numerator. I am not actually trying to reevaluate the numerator with a number that's less than 5. But if I go to my number line, I'm going to put the obvious number that's less than 5 to the left of it. And I really want to try to imagine that this is like a 4.9 or something. We want to imagine as close to the 5 as we can. For this particular example, I don't think it'll hurt to just plug in a 4. So if I plug in a 4, and we're really only interested in what happens to the denominator, as I plug that in, I get like a 4 plus 4 minus 3, square root of 4 plus 4 minus 3. So the square root of 8 minus 3. And all I really need to know is that the square root of 8 is a number that is less than 3. We're not going to use a calculator for any of these, so I just need to know that this number is negative. This is less than 0, the square root of 8 minus 3. So I'm going to think of that like a negative 0. So again, a positive number on top divided by a teeny, teeny, tiny negative number. It's not really 0, but as we approach 5, it's getting closer to 0. That's going to cause our graph to go down like that, because 7 divided by the smallest negative number you could think of is going to be a really huge negative number. So we're approaching negative infinity. All right, let's check the end behavior. We said this is from the left, or not end behavior, excuse me. I'm teaching Algebra 2 and I'm making end behavior videos. We're checking the limit from the left, and we're going to check this limit from the right as well. All right, so the limit, we're going to have x approaching 5 from the right on the number line. It's still t plus 2 over the square root of t plus 4, all that junk minus 3. We're going to keep our 7 over 0. We're not trying to do anything with that numerator. But now to the right of 5, and it wouldn't hurt to plug in a 6, but I just want to stay close to the 5, as close as I can. But let's say we do plug in a 6. Our denominator would now be the square root of the sum 6 plus 4. I think I was adding the 4 in my head to the 6, minus 3. So the square root of 10 minus 3. And again, I don't know what the square root of 10 is off the top of my head, but I know it's 3 point something because it's between 9 and 16. So the square root of 9 is 3. The square root of 16 is 4. So all I need to know is this difference is greater than 0. So again, we've got a positive number divided by a tiny positive number. And from the right, that's going to be approaching positive infinity. So as far as all we could say about evaluating this limit is the limit does not exist. We can't more specifically say that it approaches positive or negative infinity. Okay, so that's what we have to do with vertical asymptotes. And while it's not super fun, it's not super hard either, because we're never messing with the values that we get the number over 0. We're just thinking, is that denominator coming from a negative or a positive number as it gets to 0, as it becomes 0. And that's what helps us understand the behavior at the asymptote. Okay, so horizontal asymptotes are another story. A horizontal asymptote exists if the function approaches a particular value. So like in Algebra 2, just a quick flashback, when you talked about end behavior, that doesn't look horizontal, whatever. Let's just say you're talking about a nice, easy parabola. If we're talking about the end behavior, the limit as x approaches infinity, so this would be the right side of this function, I'm just going to call it f. So of this function f, we could say that limit also approaches infinity. But when we have a horizontal asymptote, we might have a function that approaches some particular value, and we need to know what that value is. So the limit might not be a positive or a negative infinity. So we could think of this again as the end behavior of the function. We will sometimes be asked to describe the end behavior, and that will be really probably asking us to evaluate a limit. So we can often just use what we know about a function, especially if it's one that comes up a lot. So let's look at this first example, this one. Evaluate the limit of the function e to the x as x approaches infinity. Well, what I would think about is that graph on page 119 that I told you want to know. All right, so this is our graph of y equals e to the x, and that ordered pair right there is 0, 1. So if we're asked to evaluate the limit as x approaches positive infinity, that's to the right. So as I look at the graph of e to the x, I can see that that graph does not have a horizontal asymptote. In fact, it goes on to infinity. So the limit of e to the x as x approaches infinity, well, we could say that it does not exist, or we could say that that goes to infinity. Let's pretend though, that we were asked this question instead. The limit of e to the x as x approaches negative infinity. So if I'm now going this direction towards negative infinity, I do need to know that I have a horizontal asymptote there at y equals 0. So just with my knowledge of the function e to the x, and it's one of the more important functions we'll work with this year, so we need to know this about it. As x approaches negative infinity, there is a limit there. There is a horizontal asymptote at y equals 0, so the limit is 0. And we use an equal sign because 0 is a number, whereas infinity is not. All right, let's see. We could evaluate the limit of the sine of x as x approaches infinity. And if I think about my sine curve, I know that the sine of 0 is 0. So my sine curve starts at 0, and that's like a single period. That's a period, but I know that pattern continues. So if I just think as I go out towards infinity on my number line, I'm not going to have a horizontal asymptote, and I'm also not going to have, like, the function's not going to go forever and ever towards infinity. So we could say that that limit does not exist. We could also say that the limit will oscillate between -1 and +1. So if I think about it, on my regular sine curve, where I haven't changed, like, I haven't performed any transformations, the sine of x oscillates between -1 and 1. So I could say that as about the limit as well. But honestly here, I think we would be fine to say that the limit does not exist. I don't think we might need to use the sine function to help us evaluate a different limit, but I wouldn't be too worried about saying anything about this limit other than it does not exist. All right, the last one is we have a cubic function, 3 minus the cube root, or sorry, it's not the cube root, I'm sorry, 3 minus x cubed. I don't know where my brain went for a second. And what I would think about is we could also consider this as like negative x cubed plus 3. So without graphing that, let's just think about what we remember from Algebra 2 for just a second. You do this test in Algebra 2. I believe you call it like the leading coefficient test. But here's how I explain it to students. Let me see if I can. I keep trying to change pen color and it's not having it. So if you have an even versus an odd exponent, so an even, for example, would be like x squared or x to the fourth, an odd like x cubed. And then we also need to consider the sign of your coefficient. So I'm going to say if you could have a positive coefficient or a negative leading coefficient. So if I think about it, positive x squared has this type of end behavior. So all even functions with a positive coefficient go up and up. Whereas if I think of the graph of positive x cubed, this is the end behavior, down to the left, up to the right. If I think about a negative even function, down, down is going to be the end behavior. It doesn't have to be x squared. It could be x to the fourth power. And if I think about an odd function with a negative coefficient, again, the end behavior just switches when the coefficient is negative, the leading coefficient. So if I look at this function and I rewrite it so that the leading term is first, the negative x cubed plus 3, the 3 is just going to tell me something about where it intercepts the y-axis. I really just need to remember this end behavior since it's polynomial. So because it has a negative coefficient and it is an odd function, this is what the end behavior is going to be like. So as x approaches negative infinity, that means we're moving to the right. Nope, sorry, we are moving to the right, but it's a positive infinity, not a negative. So that tells us we're thinking about the end behavior on the right. I can tell from just this test that I learned in Algebra 2 that that function is going to go to negative infinity. So, so the limit of 3 minus x cubed as x approaches infinity. Of course, if this is not an example of an asymptote, I just need to know that that goes to negative infinity. And again, that's based on just what we learned about end behavior in Algebra 2. All right, so in the next video, we're going to get to some of these tougher forms. When we first started talking about limits, we said there are determinate and indeterminate forms. And there's a few things that we are going to need to know about growth rates. And we'll go over those in the next video.